Hello students, welcome to Apna Tutor channel. So today's topic of discussion will be continuous charge distribution. Now what is this topic about and why we need to study this? So till now we have been dealing with two charges Q1 and Q2 and we are finding the force due to two charges or electric field due to two charges. Now what if we have a number of charges Q1, Q2, Q3 and Q and so on. So we applied principle of superposition for that, right? Now moving on to the further step, what if I have a body that is spherical in shape? It can be either hollow or solid sphere, and if I place a plus q charge on its surface or overall anywhere I can put. Now what will be the electric field due to this? So can I suppose it to be a point charge? No, we can't do it in that way. Or what happens if I take wires and if I place positive charge on the wire? So what will be the electric field due to the wire? So for that we need to understand this topic, continuous charge distribution. Now what is method that suppose we have a body and the body can either be line where the charge is distributed, or it can be a surface where the positive charge is distributed over all the surface, or it can be a volume. Okay, so now in all the three cases, what will be our method to solve? First we have to check whether our charge distribution is linear or surface or volume charge distribution. Okay, for the linear charge we will be applying lambda, that is linear charge density, which will be equal to we'll consider a small element over the surface anywhere. Okay, so that element can have a small dq charge and the length will be small dl. Okay, for so now the linear charge density for that element will be dq by dl, and similarly we can do for the surface. We'll take a small surface element which has a small dA area element and small, it has a charge dq, and similarly we can do it for the volume charge density, which we denote it as rho. So our first step was to identify the distribution whether it is linear, surface or volume, and based on that we define the small element, and with that element we calculate the total charge, or we can apply the general expression for the electric field due to the continuous charge distribution. So it is similar to the discrete charge, where now we have replaced 1 by 4 pi epsilon naught q upon r square. We have right this for the discrete charges, and now instead of q we are writing dq. Only this much is the difference. Now as we are clear with the steps and the method, now let's do one problem where we have to find the electric field. So what is the problem? Now we have to find the electric field due to rod at point P. Okay, so I have a rod and a positive charge is distributed over itself over the wire. Okay, so I take a small element and let the length of this element be dx and the charge on it will be dq, and the total length of the rod or the wire is L. So we need to find the electric field at point P. So let it be distance d, and from this point element to this P point the distance assumed is x, right? So our first step is identify, and then the second step was to take a small element. So we identified that it is a linear charge distribution and we'll be writing dq by, okay, let me write it over small q. So it will be dq by dx as we have seen earlier. So it is dq by dl, right? So this was our first step. Now the second step is to write the electric field, that is dE, electric field for the small element, and that will be k dq by x square. So x is the distance of the element from the point P. Okay, that is x. Now we can substitute the value of dq from this equation 1. So it will be k lambda dx upon x square, right? And now we have to just put the limits and we have to solve the integration. So now in order to cover the whole wire, we have to write the limits from the point P to one end. So let me call it one end. So from here to here our limits will be D, and from the point P to the another end, that will be D plus L. So while substituting the limits and solving the integration, we can get the electric field due to the whole wire. Okay, so we just need to solve the integration right now. So let's solve the integration part. It will be integral E equals to k lambda integral minus 2. Okay, so it will be k lambda 1 by x. On solving the integration, we'll get this term, and now let's substitute the limits. So minus k lambda 1 upon L plus D minus 1 by D, right? Now minus k lambda D minus L plus D, in here we'll write D into L plus D. So it will be minus k lambda. On solving, this D will be cancelled and this minus minus will become plus, and it will become D L plus D. So this will be the electric field due to the wire. Now the second we have to find the electric field due to semicircular ring. For semicircular ring, we will again perform the same steps. Okay, so first of all, let me draw the semicircular ring, and I have, since it is a ring, so the charge will be distributed over the ring. Okay, now since it is a ring, so we'll again have its lambda, that is linear charge density, right? So we'll again take a small element, let it be dq element, and the length will be dl, right? So we have to find the electric field at the center, let it be center O point, and for this point, for this element, the electric field will be radially outward, so it will be dE, right? And the angle from the axis is theta, so it will be d theta for the small element. So now we can write this dl value, right? The small length element value, that will be dl is equal to r d theta. R is this radius, we can write it. So now we can see that if this angle is theta, so it will also be theta, and since electric field is a vector quantity, so we'll resolve it into components. It will be dE cos theta and it will be dE sin theta, right? So similarly we can say it that if we have an element over the left side, again it will have electric field in this direction, so it will be again dE cos theta, and perpendicular component will be dE sin theta. So we'll see that when we'll add up all the components, that the horizontal components will cancel out and we'll left with the only vertical components. So we can write the electric field, net electric field, let me change the color, so it will be equal to dE, right? And it will be dE sine theta. So if we integrate all the dE sine theta components, we will get the net electric field due to semicircular ring. So let's write dE for the small element. It will be k dq upon r. So dq will be equal to lambda into dl, the linear charge density into length element. So we have written that dl is equal to r d theta. We can substitute the value of dl, that will be dl equal to r d theta. So let's substitute all the values. Net electric field will be k dq upon r square sine theta, right? So it will be r square. So we'll substitute the value lambda r d theta upon r square, and the sine theta will be written over here. So now we have to write the value of the limit. So it is a semicircular ring, so we'll write it from the 0 to pi. Now let's solve the integration and let's cancel out one r. So it will be k lambda by r sine theta d theta 0 to pi. So on solving, we'll get cos theta, integration of sine is minus of cos, so it will be minus over here, and we'll get k lambda upon r cos pi will be minus 1 minus cos 0 will be minus 1. So the net electric field will be k lambda upon r, it will be 2k lambda upon r. So this will be the electric field, and we can see that this is the magnitude of the electric field due to the ring, and the direction we know it's downwards, right? Now what if we have a quarter ring? If we have only this portion of the ring, only this much, so what will be the difference in the answer? So if we have a quarter ring, for that, when we'll find the electric field, this dE component, so it will be only due to this element. We'll not have any electric field on this side, since we have no element over here. We just have this much portion of the ring. So the net electric field then will be due to dE cos theta as well as dE sin theta. Then we'll get different answer. Okay, so you can try that on your own and let me know if you are not able to solve it. So this is the basic idea of solving such questions, where we have to take the element of on the body, and we have to check the distribution, whether the distribution is linear or surface or volume, and based on that we have calculate the electric field for that element, and then we'll substitute the values of the limits in order to get the net electric field. So the physics of such questions is just to take the elemental portion, and rest is the mathematical part where we have to solve the integral. Okay, so in this lecture we'll study till here, and till then keep learning. Thank you.